Hi, I'm Arianna, and I'm going to be presenting on my summer research, which is data-driven multi-phase pressure drop relationships under the guidance of Professor Tiagi and Dr. Jang. Multi-phase flow through pipes is important for the oil and gas industry to prevent accidents or maintain equipment. And we want to predict the pressure drop using machine learning, and we are going to simulate the steady state multi-phase flows. Multiphase flows occur in almost all wells that produce oil and gas and in the pipes that are transporting these fluids. So there have been many efforts to model multiphase flow in pipes, the first being an empirical approach that involves flowing fluids at carefully measured flow rates, observing the flow patterns, which are the patterns between the gas and the fluid that we can see in these pictures, and measuring liquid holdup and pressure drop. We can also change some of the parameters like the diameter of the pipes, the incline, but the measurements are steady state. And the other approach is a modeling approach that uses an empirical approach, the measurements from that, and builds a model to help further understand how multiphase flow works in pipes. So here is an open foam simulation of the multiphase flow. So the red is the fluid and the blue is the air or gas that's going through the pipe. And in this first image, we can see the pockets of air. So this is a plug flow. When we increase that air, we have more of a slug flow. So these are technically like really large pockets. And then when we have even more air, this is an annular flow. Dr. Jang has helped me by making some simulations in open foam. So he set up a pipe that is 4.4 meters long and has a 0.02 meter diameter, and water is being sent upward vertically through the pipe. And at a 45-degree angle, there's air that's being sent through. These are our simulation parameters. The velocity of the water is 0.07 meters per second, and the velocity of the air ranges from 0.2 to 0.7 meters per second. So here, alpha represents the mixture fraction. So at 1 or red, it is all water, and at blue or 0, it is all air, and everything between is the mixture of both. So we can see here at the lower range of velocity of the air that there are pockets of air going through. And if we increase the air to the largest end of the velocity, there's just a lot more air and it's harder to see the red in the pipe. Once we have our data, we can process it. So we're going to select locations along the flow of the water, and these are going to be our end stations, and this corresponds to the number of nodes in our pressure drop equation. So here we decided to choose 10 stations. Next, we determine the average pressure and volume at each station, and then we write time series for the relevant variables. So in this case, this is the time series data for pressure along 10 different stations. And we will run this for different mixture fractions. So for our velocity, we're going to run this multiple times for a velocity of air from 0.2 meters per second to 0.7. Once we have our time series data, we're going to build long short-term memory networks, LSTM networks. And here we can see a model of the LSTM network. So this is our previous state, our current state, and the time state we want to predict. And long short-term time series are great because they remember the series, but forget the previous state. So here is a closer look at one of the memory cells, one of the cells in the LSTM network. So we have information coming in from the previous time step, and it goes to the forget gate, and that decides what wants to be forgotten. So that's the short-term memory portion. Then the what wants to be remembered goes to the input gate and is transferred to the cell. And that's the memory cell that's remembering the series. It then goes to the output gate that takes into consideration both of these before moving on to the next state. This is also what I spent a majority of my summer working on, and I started using shampoo sales data to get accustomed to the model, and am working towards finishing that to then move over onto the pipe data. So I'm going to explain my shampoo sales data. So when we have our data before building the model, we want to prepare it. So the first step is transforming a time series to supervised learning, which means separating the data into inputs and outputs. So if we look at this image, this is our previous time step and our current. So this is our input and this is our output. So that's what we're doing here. And then we want to split the data set into two parts, a training set and a test set. So the training is used to help build the model. And then the test is kind of just to perfect our model. And once we have a good error, we can move on to predicting. So in our case, we used 2/3 of the data for training and 1/3 of the data for testing. Before I go into really discussing the model, I want to emphasize again that among different recurrent neural networks, LSTMs forget the state but remember the series, which allows for larger learning with larger time lags and time steps. And also means that there's less memory, so it's able to process a lot better. So when building the model, we want to reshape the input for the LSTM layer into samples, time steps, and features. Samples are the number of rows of the data. Time steps is the number of times that we want to feed the data to the model. And features is the number of columns of the data. We then have a single hidden LSTM layer with neurons. So the neurons are the different memory pieces that will be processing the model. We then have a dense layer that takes care of the outputs, and then a compiling network with a specified loss function. So in our case, we're working with root mean square error and an optimization algorithm. Once we have the model built, we can move on to making our predictions. So again, I had, with my shampoo sales, I had a few months worth of shampoo sales data for 3 different sales. And here we can see the predictions for each. And this is what the model prints out. So this is just the end of the data from months of July to December. We can see the predicted and expected sales along with a root mean square error. My college requires that I do a thesis for undergrad. And so I will be continuing my work with Professor Tiagi. And once I have the data, the LSTM data for the pipes, I will transfer over to the physics-informed neural networks. That will help me minimize the loss. And once I have my variables with minimized loss, I can then move on to predicting the pressure drop using the pressure drop equation. And yes, this is my presentation. Are there any questions?
Yeah, I have a question. Why did you use the shampoo data?
Well, it was just, so there's this guy, Jason Brownlee, that does a lot of different things with long short-term memory networks. And the first one I saw was, or the first one that Professor Tiagi gave me was on shampoo sales. And it was single variable, so it was only one sale. And he told me that with the pipe data, it's multivariable. So I want you to expand this model and it'll help you kind of just like change everything to make it for more variables. And once I have the pipe data, I would kind of already know how to navigate. So there's no real particular reason. It's just he was like, here's this first example. And I was like, okay, I understand that example. I'll make that work.
Okay. Nice.
Thank you.
Any question, comment? Everybody's very shy today.
So I have a question.
Yeah, go ahead.
So can you go back to the slide where you had the shampoo data, the table?
This one?
Yes. So it wasn't clear to me how well your model was doing there. Can you?
It is not, it still has a lot of tweaking to do, but this is kind of just like what I've accomplished so far. So it's like able to make predictions and like have the expected sales and calculate some sort of error. And this is like the comparison of both the expected and predicted, but it still needs like some tweaking because there's just a lot to building the model and a lot of parameters that I have to change. And so it's kind of just showing my progress with that.
Okay, thank you.
More questions? Okay, there is no any other question. Let's thank Arianna.